Hey guys, Mr. B here, and in this video we're going to be going through the chapter 5.1 notes on models of the atom. So in this section we're going to be taking a look at the new and current model of the atom, or at least its progression. So the last time that we talked about material, we had talked about Rutherfords Model of the atom. That was where we left off in chapter 4. And we're basically going to start from there and kind of work our way to the current model of the atom, and again, why we had to make changes to it and how we got to where we are today. So, first off, let's talk about Rutherford's model of the atom and what was wrong with it, okay? Now, if you don't remember what Rutherford's model of the atom looks like this. It's basically what I like to call the Jimmy Neutron model, right? Where you have the nucleus in the middle and you have all the electrons kind of buzzing around the nucleus, or like planets that orbit around the sun. Again, if you were to ask anybody to draw a picture of what an atom looks like, this is probably the picture that they would draw you, or some version of this, right? Where you have the nucleus and all these electrons that kind of go around. Now, this isn't necessarily a bad model, okay? It was better than anything that we had at the time because it included all of the different subatomic particles, both protons, neutrons, and electrons. That was important. It also accurately put where at least they are in the atom in relation to each other. So it put the protons and the neutrons in the middle, called the nucleus, and it put the electrons outside the nucleus, and there's a lot of space in between the nucleus and the electrons, which again was very important because that had never been determined up to that point. So it was a really good model for its day. However, there were some flaws to it. The biggest flaw was that his model, other than maybe showing or kind of representing where particles were, wasn't very good at actually describing why atoms did the things they did, or why elements behaved the way they did in terms of their chemical properties. And this is something that in science especially, we want models that are functional. So maybe when you think of the word a model, like model, you think of a physical representation of something bigger, and it's just a small version, right? Like a miniature building or a miniature airplane or something. And certainly those types of models are helpful, but we want models that are more functional than just simply being a visual representation. We want models that not only can visually represent something, but also can be used to like determine and predict things in the future. So the model that Rutherford came up with didn't account for why do elements behave the way they do? Why do they have certain chemical properties? How come these elements all behave very similar and these elements all behave very similar? And how are they different from each other? Rutherford's model kind of broke down at that point. And one of the biggest ones and biggest questions that people had at the time was, why do metals like iron, for example, when we heat it up, why does it go through this different phases of color? Like when you heat up a piece of metal, why does it go from like a deep red to like an orange to yellow and then to glowing whites? Like, why does it go through this range of colors, right? They wanted to know why that happened. So we had to have a new model of the atom proposed to essentially answer that question. And so far, this is what we had at the time. So first we had John Dalton's model, which was just basically a sphere. Then we had Thomson's model, which is the plum pudding model. Then we had Rutherford's model. And from here, should be shows. And from here, we then jump into what we call the Bohr model. So this model, the atom, was proposed by Niels Bohr, who was a physicist. I think he was Austrian, but I could be wrong there. So either way, his model, we'll talk about here in a second, basically tried to account for the reason why things change colors when you heat them up, and what was happening. And then from there, we go into the current model, which is called the quantum mechanical model. So let's first, though, talk a little bit more about the Bohr model of the atom, okay? So what is the Bohr model? Who is Niels Bohr? What is he talking about? So Niels Bohr basically proposed this. So he said, okay, there's a nucleus. There are electrons that are around the nucleus. However, they don't just kind of buzz around the nucleus and go around in circles like whatever they want. They are in specific places called orbits. Okay, so like planets orbit around the sun. They're in a very specific place, and they go around the nucleus at very specific distances called orbits, okay, in these circular paths. And what can happen is when electrons are in these paths, these orbits, they have a very specific amount of energy, okay, and that energy is fixed. So it can't change, or at least it can't fluctuate. So I'm going to call this an energy level. So these orbits, as they go around the nucleus, are certain amounts of energy. I'm going to call them energy levels, and electrons have so much energy. And his proposal is when you heat up an element, or you heat up a metal, the electrons will absorb energy from the heat. And when that happens, if they absorb enough energy, or a very specific amount, which he called a quantum, they will jump from one energy level, or one orbit, to a further one, or one that's bigger, further away from the nucleus, right? So they may start down here and like close to the nucleus, then absorb energy, and then they jump to this one, and now they're further away, okay? And when that happens, electrons don't want to be energized. They don't want to have that energy. So what they will do is they will release it right away. So absorb the energy, they'll jump to a higher energy level, and then they'll release that energy, typically in the form of light. And the amount of energy that they absorb and release will then be specific to a certain color of light that you'll see with your eyes, such as red, or orange, or yellow, or green, or white, or purple, or blue. And so these electrons just kind of keep doing this. So you heat something up, electron absorbs energy, jumps to another energy level, releases that energy, falls back down, and then it absorbs energy again, jumps back up, releases that energy, falls back down, and it does this over and over and over, and it does it so fast that all you see is just a continuous color of, oh, it's just red. But technically it's actually like doing this over and over and over and over really, really fast. So, but your eyes just, you don't see it because your eyes can't see things that fast. So that was his proposal. And it was a pretty radical idea, but it makes sense, right? Now, one thing he mentioned was that these energy levels, think of them like rungs on a ladder. So in order to go from one energy level to the next, you have to have an exact amount of energy to get there. Kind of like if you're going to climb a ladder and you're going to lift your foot to get to the next rung, you need to lift your foot a very specific amount of space. And if you don't lift it high enough, you're not going to get to the next rung, right? Your foot will fall right back down to where it started. Also, if you give it too much energy, that extra energy just goes to waste, because once you hit a certain amount, you'll get to the next energy level, and anything over that, unless it's enough to get to the next one, just goes to waste as the electron falls down to whatever energy level they reach, right? Again, same thing like a ladder when you're climbing. If you lift your foot above the next rung, but not high enough to get to the one after that, your foot's just going to fall down and it's going to land on this rung anyway. So basically, like, electrons will absorb a very specific amount of energy, and if you don't give them enough, they won't make it. If you give them too much, the extra stuff just goes to waste. But as you get higher and higher on this ladder, okay, the energy levels, the spacing between those rungs gets smaller. So the biggest jump is from the ground to the first rung, and then from the first rung to the second rung, but then from the second one to the third one, it's smaller, and the third one to the fourth one is smaller, and the fourth to the fifth one, it's even smaller. So as you get higher and higher, the amount of energy needed to get to the next energy level gets smaller and smaller and smaller. So it's easier to jump at higher energy levels than the low ones, okay? So again, this is pretty radical, but it helped to explain what was going on. Now, this model then basically looked something like this. Let me pull it up here. Pull up the Bohr model of the atom. So we have, again, these orbits where the electrons can go, and they absorb energy. So n equals 1. This is energy level number 1, okay? So maybe this electron is in the first energy level. It absorbs energy and jumps from energy level 1 to energy level 2. So basically just jumps further out. And then, of course, it releases that energy in the form of light, and that light might be red in color. It falls back down to the first energy level, and then it does it all over again, okay? Now, the key thing to note here is it actually jumps from one energy level to the next. It doesn't move, okay? It's not like it's going here and then it like just moves out. It actually ceases to exist. It's either in the first one or the second one, and it cannot be in between at all. This is a really weird concept, and it doesn't make a whole lot of sense to our regular brains, because this doesn't happen on the scale that we live at in the world around us, but this is how electrons work. They either exist here or here, and there is no in between. And you might ask, well, how do they go from there to there? They literally just go and they jump. They cease to exist here, and they now exist here. Again, high-level physics concept, but regardless. So this is what the Bohr model looks like. It's basically a nucleus with a bunch of circles around it. And there are an infinite number of energy levels. So there's no like maximum number of rings that you can have around the nucleus. Like it goes from 1, 2, 3 all the way up till infinity. Okay, and we'll talk about these later on. So, all right. So from here now, of course, this is not the current model of the atom. Okay, we have a different model today. So the question then becomes, well, what was wrong with the Bohr model, right? Like if it was able to describe chemical properties and all this stuff, why did we have to change it? Why do we have a different one today? Well, it's because his model didn't accurately show how electrons move. So the quantum mechanical model, which is the current model of the atom, basically was an attempt to try to describe how electrons moved and also to help describe chemical bonding. Electrons in the Bohr model go around in circles like this, right? And they can't go anywhere else. It's either this circle or it's in this bigger circle or it's in a bigger circle, but they're flat, right? They're two-dimensional. And of course, we know that atoms are not two-dimensional, they're three-dimensional. So the quantum mechanical model helps to describe those orbits in 3 dimensions as well as where they're found around the nucleus, because they're not found in just circles like this, okay? So the quantum mechanical model basically determines that electrons have an allowed amount of energy, but you can't ever know exactly where they are. So the quantum mechanical model says, all right, you don't know if the electron is moving around in a circle here, okay? There's just a probability that it's there, but it could be somewhere else. Again, very weird concepts. And we're going to talk a little bit more about this here in a second. So this model was proposed by Erwin Schrödinger, again, Austrian physicist. It's basically based on mathematical equations. So it's kind of hard to draw this model out on paper because it's really funky and it gets really messy. So, but he called it the quantum mechanical model. And again, we're going to talk about what exactly it looks like and how it works. So before we do that, I want you to take a look at this picture of this airplane, right, with these propellers that are spinning. And I want to ask a question. You want to propose a question. The question I have is, if you look at this picture, could you tell me exactly where these propeller blades are currently right now in this picture? You're probably gonna like think to yourself and go, well, yeah. I mean, it looks like maybe one's here. And like one's there because say there's these like black spots there, these black lines, so that's where the propellers are. I mean, you don't know that for sure, right? I mean, there's also this blurry region here where these propellers could be too. Like just because there's black lines, it doesn't mean that that's where the propellers are. You're just making a guess. To be honest, the answer is there's no way of knowing. There's no way of determining where these propeller blades are exactly currently right now in this picture. However, we do know that they're going to be somewhere in this general region, right? Like the propeller blade's not going to be found back here at the tail of the airplane. It's going to be somewhere up here. This is the same premise when it comes to electrons around atoms and the nucleus. The quantum mechanical model basically says you don't ever know where you can find an electron. The only thing you can do is have a probability of where you can find an electron, but you'll never know exactly where it is. So the quantum mechanical model basically it works based on probability, and it has what we call electron density clouds. So imagine that again, this is the nucleus, and this fuzzy region of space is a region of space where you have a high chance of finding an electron. Okay? And the darker parts of the cloud, you have a higher probability, and the lighter parts of the cloud, you have a smaller probability. So it could be that like maybe if we were to ask, where is the electron currently right now around the nucleus? We could say, well, I would say about 95% of the time, you're going to find it in this dark region of space, somewhere in this region. Maybe like 4% of the time, you'll find it maybe out in this lighter region. And maybe like 0.9% of the time, you'll find it on the very, very edge. And then anything beyond that, you have a chance of finding it too, but it's like 0.0001% that you'd ever find it somewhere out here. And this is essentially what the quantum mechanical model says. So it takes the two-dimensional orbits of the Bohr model, and it instead now says, okay, we have a three-dimensional region of space, and now we have probabilities of finding electrons. And you might ask, well, why do we need probability? Like, why can't we just say the electron's right there? It's like right here, right? Because it doesn't work that way. In fact, just the act of trying to take a picture of an electron will move it to a different location. Okay, so like when you take a picture or you use a sensor to take an image of something, a lot of times what we do is we'll send light particles or some kind of wave out, will hit the object, and then that will bounce back and hit the sensor, and then the sensor will get an image of like what that thing looked like, okay? It's basically how your eyes work. It's how cameras work. Light has to come in. It has to hit your retina or your sensor on your camera, and the camera can make an image, or your eye can make an image with the brain, and then bam, you see something. Well, the problem is with electrons, they're so small that if you send something out like energy or a wave or a particle to hit the electron and bounce back to then get an image, just the act of hitting that electron with that particle or energy and then having it bounce back will move the electron somewhere else. So the image you might get will go, oh, there's the electron. It's like, well, no, that's where the electron was. It's not where it is anymore. Now it's somewhere else because you moved it. Well, I'll just take another picture. Okay, cool. Take another picture. Boom, you hit it, comes back. Oh, now it's over there. No, that's where it was. Now it's somewhere else. You do this 1,000 times, and basically what you're going to get is you're going to get an image of all these places where the electron could be, but you'll have no picture of where the electron actually is, right? And that's, again, what the quantum mechanical model basically says. This is known as the Heisenberg uncertainty principle. All right, so let's talk about the quantum mechanical model and essentially what are the main components of it, okay? Now, the vocabulary here is going to get a little bit tricky, so I'd recommend during this part that you really pay attention to the vocab and maybe write some things down here. So, in the quantum mechanical model, we have orbitals, okay? Now, in the Bohr model, we had orbits, and just to clarify what the difference, okay? So, orbits, in this picture here, orbits are two-dimensional circles, right? Like planet Earth orbits around the sun, or Mars orbits around the sun. An orbital, however, is a three-dimensional region of space. So, to pull up a picture here to show you what I'm talking about. So, an orbit would be a two-dimensional circle, right? 2 dimensions, that's a circle. An orbital, which is three-dimensional, would be a sphere, right? You have a sphere. Things can go around in the sphere. So, the quantum mechanical model has orbitals, which are three-dimensional regions of space, where there's a high probability of finding an electron. And each energy sublevel, which is orbitals, okay, correspond to a different orbital shape, which is where we can find electrons. So basically, again, we'll take a look at what this means. So we have energy levels, and we have sublevels, and we have orbitals. And again, this is where the vocab can start to get tricky. So I'm going to try to explain it as best as I can. So we have different atomic orbitals, okay? We have s orbitals, which are spherical. We have p orbitals, which are peanut-shaped, okay? They're not named p orbitals because they're peanut-shaped. It just happens to be peanut-shaped. They stand for something else, but regardless, okay? Each one of these is a different sublevel. So inside of one energy level, you might have an s orbital, which is a sphere. Then let's say this is the first energy level, okay? So you're going to have a sphere that's like this big. Then you'll have another sublevel. Let's say at energy level 2, you have another s orbital, but it's bigger, right? Because the second energy level is essentially just a bigger ring. So energy level 1, your sphere is this big. Energy level 2, your sphere is this big. So this is what we call 1s, energy level 1, s-shaped orbital. And then 2s, energy level 2, s-shaped orbital. Okay, and your sphere is just bigger. That's a sublevel. Then, of course, you can have energy level 3, where now your sphere is even bigger. That's another sublevel. And then energy level 4, where your sphere is even bigger. That's another sublevel. Okay? So sublevels are basically within energy levels, and they're the different shapes of the orbitals that you have. You can say you have the same thing with p orbitals. Then, of course, you have your d orbitals, which are four-leaf clover shaped. Okay, now the main thing to note here is how many different types there are. So with s orbitals, there's only one type of s orbital. Every single one is a sphere. For p orbitals, there are 3 types of p orbitals. Each one is on a different part of the Cartesian plane, which is the axes that you're used to, like the x-axis, the y-axis, then the z-axis, which is the axis that goes straight out and straight back. So the z-axis is the one that makes things three-dimensional, hence 3 dimensions, right? X, y, and z. Then d orbitals, there are 5 d orbitals. They basically look like 4-leaf clovers or x's, other than this one over here, this dz squared. It's sort of like a p orbital with a little donut around the middle. And then the last ones we have, and these are not actually mentioned here, but I'm going to type them out anyway, are the f orbitals. You don't need to know what f orbitals look like because they look really weird, but f orbitals, there are 7 f orbitals. Okay, and we'll talk more about f orbitals later, probably in class, but they are, at least again, ones to know about because they will pop up. So, okay, so the number and kinds of orbitals depends on the energy sublevel. Basically, at energy level number 1, you have one sublevel, and that is just a 1s orbital. Okay, that's a sublevel, just the type and shape of orbital you have. At energy level 2, you have 2 sublevels. You have 2s orbitals, and you have 2p orbitals. Okay, so one sublevel is the 2s, that's the sphere, and another sublevel is the 2p, so those are all the peanut-shaped ones. At energy level 3, you have 3 sublevels. You have an s orbital, sphere. You have p orbitals, right, peanut-shaped. Then you have the d orbitals, which are all 4-leaf clover looking. And then at energy level 4, you have 4 sublevels. You have your s orbital, which is a sphere. It's just a bigger sphere. You have your p orbitals, you have your d orbitals, and you have your f orbitals. And then there's nothing beyond the f. So at energy level 5, principal energy level 5, technically you have 5 sublevels, but on the periodic table, we're never going to go above f. So you don't need to worry about anything beyond f. Okay. This chart here has the maximum number of electrons that each sublevel can hold. We'll talk more about this in the next section. We're going to learn about some rules of orbitals and how many electrons they can hold. So for this, I would just don't worry too much about this other than just know it's here. And if you need to find it, you can find it. So, okay. So that is it for this section. And again, you might have some more confusion. So make sure that you ask some questions. There are other videos in the helpful videos folder in the chapter section in Schoology. Utilize those videos. I can tell you that they will help you a lot because, again, we're talking about some concepts here that are confusing. Okay, we're talking about physics that is sort of theoretical and very strange. So if you have confusion, just make sure you ask. I will probably clarify things in class as well, but it's also on you to make sure that you get those questions answered. So, all right, guys, I am Mr. B. Thanks for watching. I'll see you in the next one. Bye.